أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم سبحانك لا علم لنا إلا ما علمتنا إنك أنت العليم الحكيم. Assalamu alaikum dear students. Today we're gonna do the 11th lecture of operating system. In this lecture we'll discuss the classical problems of inter-process communication or IPC. So classical problems of IPC. There are three problems that we'll call IPC or inter-process communication problems. The bounded buffer problem, that is also known as producer-consumer problem, and the second was reader-writer problem, and the third one is dining-philosopher problem. So these are the three problems that will be discussed in this lecture as well as in the next lecture. So the reader-writer problem, the bounded buffer problem, that is also known as the producer consumer problem, and finally the dining philosopher problem. So first we'll discuss the bounded buffer problem. There is a fixed size buffer. It means that in producer consumer problem there exists a fixed size buffer. A fixed size buffer means that the size of the buffer cannot grow or shrink when the process executes. Right, and it consists of n slots or n locations. There exists n location in the input buffer. The producer process produces a character. It can be a character or other units that can be placed in a slot. It can be a word, a byte, a kb, even an mb, but it can be placed in the single slot of the buffer. So for example, if we have a buffer that consists of two slots, for example, then every time when a producer process produces some input, then that input will exactly fix the one of the slots, right? And one slot will be filled with the input that is produced by the producer process. And similarly there is another process that is consumer. So this process was basically producer, and that was producing character and placing in the input buffer. And secondly we have another process that is consumer process. So consumer process basically reads the data from the buffer, but once it reads the data, it reads a complete chunk of data that is located in a single slot. So in a single read operation, it reads the data from the slot, from one slot, right? And for that reason we can say that slot size must be equal to operational data unit that can be read or write operation. So in one read, for example, if a process produces one character, so the consumer must read only one character in one read operation. And every slot of the buffer will consist of slots that can only hold one character. But if both of these processes are running in parallel, then synchronization problems can result. And we'll discuss in a little while that how these problems are generated basically. So producer maintains a pointer which points to the next empty location in the buffer. Producer process basically maintains a pointer, right, which points to the next empty location in the buffer, because it is placing character in the buffer, so it must maintain a pointer that will point to the next empty location so that the next produced input can be placed on that location, while consumer maintains a pointer which points to the location from where read operation is performed, or from where the read operation is going to be performed, right? So the consumer process maintains a pointer at points to the, in a buffer that from where the data should be read. Similarly, in addition to these, both processes maintain a common variable, and that variable is count. So the count variable basically shows that how many data items are there in the buffer, how many slots are filled. So how many slots are filled, or how many data units, data items are there in the buffer is used using count. And now you can see that count variable is a shared variable, because once a data is inserted in the buffer, then producer problem will have to increment the counter variable. Similarly, once the data item is read from the buffer, then the consumer process will have to decrement the count. So count is basically a shared variable, and it is simultaneously maintained by two processes. So it is possible that some order a race condition can result, and how this race condition can result we'll discuss just in the slide next to this one. So the synchronization problem occurs due to simultaneous change being made in the count variable. If two processes simultaneously changing the count variable, for example consumer wanna decrement it while producer wanna increment it, so in that situation there can be an inconsistency in the value of the count variable. Now let's understand how things happen. So for example, we have two processes P1 and P2. P1 you can see here is a write and is a read process or is a consumer process. So it is basically consumer process, and P2 which is basically the writer, or we can say it is a producer problem. So P2 basically produces characters and plays them on the input buffer, and similarly consumer or P1 reads data from the buffer. And for example here is the buffer which with a fixed size 10, and similarly we have multiple characters with P2 or the producer problem. So producer wanna produce this character, and at the same time I have an n variable or n pointer which points for the producer that where the next character should be placed. Similarly we have an out variable or out pointer which points for the P1 that from where should read operation be made. And similarly we have a count variable that counts the number of filled slots in the buffer. So for example in the first instance P2 generates a and it places it at n pointer, and because a has been placed in the buffer, now it has to increment the counter. So counter is equal to 1, and similarly it will have to move ahead the n pointer. It will shows that where the next character will be placed. Similarly for example b is generated, and once b is generated it is inserted in the n pointer, and similarly it will have to increment the count. So count is equal to 2 now. It shows that there exists two characters in the input buffer, and similarly an index will be incremented. And now for example third character is generated by P2 and is placed in the buffer, and similarly counter is incremented and n operation or n pointer is increased. Similarly now at this moment D is generated, another character is generated, it is placed in input in the buffer, counter is incremented and n is moved ahead. And now for example at this moment P1 reads A. Once P1 reads A, then what it basically does, it has to decrement the count variable. So count has been reduced to 3, and similarly it will have to move the out pointer one step ahead. So out has been moved one step ahead, and this way for example another character generated and placed in the buffer, count is incremented and n is moved ahead. Similarly another character generated, placed in the buffer, and count is incremented and n is moved ahead. At this moment for example g is generated, placed in the buffer, and count is incremented and n is moved ahead. Now for example we generate another character that is placed at n pointer, and at that moment count is incremented. Now and the n pointer will be incremented. At this moment for example both P1 and P2 execute. Alright, so P2 basically generates this character and places it in the buffer, while at the same time P1 reads this one, and both pointers that are in and out are moved one step ahead. Alright, and what is now it is a time to basically increment the count and decrement it, but simultaneously, and you know that simultaneously it cannot happen. And for example if I'm here and I say that first the previous value of the count was 8, sorry 7. So for example, this process runs first and it increments the count variable, and now it becomes 8, and soon after that this process executes and it renders the value 7. It's simple. So there is no issue with, because one element has been removed from the buffer and one element has been read from the buffer. Or in another let's change the order. So as the previous value of the count was 7, here you can see the previous value was 7, and for example p1 runs first followed by p2. Once p1 runs, it changes the value to 6, because it decrements the value of the counter, and followed by p2, which increments the value of count, and now it's become 7. So there is no issue with the concurrent running of the count variable, but the thing doesn't happen in the way we are thinking. There is no synchronization between P1 and P2. P1 and P2 basically when they run simultaneously, then the operation count plus plus, for example operation of this is count minus minus, and operation for this is count plus plus. So an assembly language, it further consists of 3 sub instructions. Here you can see these instruction and this piece of code, that to increment the count variable, we first move the count variable to a register, then we will add 1 to the value of the register, and then that register is moved back to the count variable. So further 3 steps are required to increment the value of a counter. And similarly to decrement, first count is assigned to a register, then 1 is subtracted from the value of the register, and finally that register value is copied back into count. So count plus plus and count minus minus are not atomic operations. In assembly language, they further consist of 3 sub steps that must be performed, and once they are running in concurrently, so the problem arises. And here you can see that, for example 7, that was the initial value of the count. So at the same time 7 was assigned to this register, as well as 7 was assigned to this register. Then this value has been incremented and register plus 1, so the register's value become 8 here. Alright, so register value become 8 here, and here you can see that register value become 5 here. Now register's value is 5. And at this moment, as though we are saying that both of the processes are running concurrently, but to put a value in a variable basically cannot happen simultaneously, and in the operation which is performed, the last will exist. So for example, this operation is performed first, so the increment operation basically leads the value to be 8. So count is equal to 8 here, and soon after the completion of this statement, the another decrement operations last statement, this statement is executed, and again the count value is overridden, and count is equal to register. So register is now 5. Register is now 5 in this instruction, so 5 is overridden in this, and final value that we'll get as a result of concurrent execution of C minus minus and C plus plus will be C is equal to 5. Our count is equal to 5, and you can see here that it's not consistent. What we actually need was that we need the value of the counter to be 7. 7 was the right option. And in contrast, for example, if this statement runs first, then it will make the counter will be equal to 5, and followed by so let me write this one first. So count is equal to 5, but soon after that this statement is executed and it assign 8 to the counter. So 8 is assigned to the counter. It means that the previous 5 will be erased and 8 will be overwritten on C, and now the final value will be 8, and that is also incorrect. That is also incorrect, because what was the correct value? The correct value was 7, and that is not uh, uh, happen in this variable. Now another character generated, and in this context n is be in cyclic fashion, because you can see the codes of these two processes, and similarly this is the code for producer and here is the code for consumer. For further detailed explanation of these code, you can watch my previous video of process synchronization part 1. In process synchronization of part 1, I have discussed process synchronization of two processes. That was the lecture started. So this is the code for producer process and this is the code for consumer process. The producer process basically first check if the buffer size is full, then it will wait. This semicolon shows that this process will wait, and once the next character once the condition become false, then next character is produced and it is inserted at the n pointer, and then n pointer is incremented, but it's not a straightforward increment, it is cyclic increment. It means that when once n reaches here, it is moved back over here, right? So in a cyclic fashion, this pointer is incremented. And similarly you can see that for consumer process, it will check if the list is empty, then it cannot consume anything, so it will wait. And again, if there is some character, then it will read that character and print that out, and then it will move its out pointer ahead, but in a cyclic fashion, because it's the remainder with this buffer size, and eventually counter will be decremented. That will show that how many characters or how many inputs data are available in the buffer. And if this particular order, if the statements or the above statement of the assembly language are executed in this particular order, then you can see that there will be inconsistency in the final value, because one process will say that it's 7 and another process, one process will say it's 5 and another process will say it's it's 8. One process will say it's 6 and another process will say it's 5. Now now that we have found that there exists inconsistency in the final value of the count in the previous implementation, although it was seen to us that there is no issue, but once we enter in the detailed programming concepts and we traced that code into assembly language, then found that there can be inconsistency in the final value of the counter, because counter plus plus and counter minus minus can be executed simultaneously, and that will lead to the inconsistent data. So so how can we solve these issues? So we have multiple options in the Peterson algorithm, because can we? Yes, because Peterson algorithm was basically to deal with the two processes, and these are the two processes, and the only problem is mutual exclusion. So mutual exclusion problem can be solved with the Peterson algorithm. Similarly with Backward algorithm, yes, we can do with Backward algorithm, although the Backward algorithm was more general and more complex in nature and was for multiple processes, but it was also applicable for two processes. And similarly with binary semaphore, we can do that, because binary semaphore ensures mutual exclusion, and here the critical section is counter plus plus and counter minus minus. That is the critical section. So if we sandwich that particular section with weight and signal and mutex a semaphore, then we can be able to solve this issue. And with counting semaphore, with counting semaphore, we'll have to count is equal to buffer size, or another way is to count with the counting semaphore is to initiate count is equal to 0. The first will show count is equal to buffer size, means that it ensures that we are not reading from an empty buffer, and we are not inserting in a full buffer, right? And then this one count is equal to 0 means that we cannot produce character in a full buffer. Now let us discuss using binary semaphore. How with the use of binary semaphore we can resolve the producer consumer problem. So here is the code for producer, and you can see that while true, counter is equal to buffer size. If counter was equal to buffer size, it means that the buffer is full, so we cannot produce another character, so we will wait at this semicolon shows that this is an empty body. It means that we will wait here, and once there's the space is available, then we will have to produce next character and place that character in the at the end pointer, and then what we'll do is basically increment the end pointer in a cyclic fashion, remember, in a cyclic fashion. And finally what we'll have to do is to increment the counter, and the counter value will be incremented. Before performing this thing, the value of the counter will be 0 because there will be no character at the start of the processes. And here is the code for consumer process. The consumer process, it will first check that if counter is equal to 0, that means that there is nothing to read, then the process will wait, and if something is there to read, then it will read there out that, and it will increment the out pointer with in a cyclic fashion, and finally it will have to decrement the counter variable. Now what we will actually do while for solving this problem, what we will actually do to resolve this issue or to solve this problem, we are just finding the critical section that where actually the problem lies. So the problem lies with the increment operator of the producer and the decrement operator of the consumer. So we can sandwich these two statements with a single binary semaphore. So the binary semaphore that I call it Mutex. So before before performing the increment operation, I will call wait on Mutex, so that this piece of code will be logged, another process will not be able to execute that piece of code. And once I leave that increment operator, similarly in here in this consumer problem, once I am entering in the counter minus minus, or I am entering in the decrement of the counter, so I will call wait on Mutex, and once I leave that counter, I will have to signal the Mutex so that another process can be able to access the counter variable. And similarly in the producer problem, once I done with counter plus plus, I will have to signal Mutex so that other processes can enter their critical sections. And here is the animated way that how basically this solution works. So we have two processes, P1 and P2. Here you can see that P1 is the consumer while P2 is the producer or writer, right? So it is basically producer. And here is a fixed size buffer that consists of 1 2 3 4 5 6 slot buffer size, and these are the variables that will be initially declared, and this end pointer shows that where the next character will be inserted. Similarly out pointer shows that where the next from where the next character will be read, and similarly counter variable shows that how many characters or how many input slots are fed, and mutex is the mutual exclusion variable semaphore that just shows that when to enter when to allow a process to enter the critical section and when to prohibit that process. So for example a process P2 produces a character A. So producer produces a character and places the end pointer, and now it increments its pointer. End pointer is being incremented. You can see here in this statement that increment is performed, and now it will have to execute wait on mutex. Okay, so once wait on mutex is called, then you can see that the mutex value is not 0, it is 1. So it will easily enter the wait function and decrement the value of the counter, increment the value of the counter. So counter value will be incremented and mutex will be set to 0 back. Mutex will be 0, it means that now it has been entered in the critical section. Now the process is executing the increment operation, means that process in this operation, and performing this operation it will increment the counter variable. So now counter is equal to 1, and once it leaves its critical section, then it will have to execute signal on mutex, and if it runs signal on mutex, it means that it is basically incrementing the value of mutex. So mutex value will become 1. Now suppose another character is generated by P2. So once P2 produces a character, it is placed in the input buffer, n pointer is incremented, and because you can see that now the process has incremented this n pointer, so it will have to increment the counter variable. But as you know, as we noted previously, that counter is the critical section, so it must execute wait function. So wait on mutex. So once wait on mutex is executed, value of mutex is reduced to 0, and at this moment p2 is in a critical section, that will increment the counter. So counter variable will be incremented and counter will become 2. Now if it leaves the critical section, then it will have to call mutex and signal on mutex, and mutex value will be incremented and it will be 1. Now suppose at this moment both processes P1 and P2 wanna do something. P2 wanna insert some character while P1 wanna read some character. So at this moment both are simultaneously basically happening simultaneously, and both are checking their respective conditions in the first statement, and they found that these conditions are not true. Once these conditions are not true, then producer will produce a character and place an n pointer, while consumer will consume a character and print that out. So here is the thing, that C is being produced by the process P2, while A is being has been read by P1. Okay. And now both of the processes are the consumer process will have to increment its out, and the producer will have to increment its in a cyclic fashion. So both of them will move ahead in this way, and now both of them will try to enter the counter the critical section, this and this. At this moment, as we said earlier, that and semaphore, these are atomic operations, so wait will be called by both operations. For example, wait of producer and wait of consumer are being called simultaneously, but as we noted that they cannot enter the wait function simultaneously, so one will enter, another will not enter. So for example, first the wait of consumer is entering, so in this case it will have to set the mutex first, because wait on mutex is called. So once wait on mutex is called, then value of mutex will be decremented, it will become 0, and upon 0 it will enter the critical section, counter minus minus, and counts value will become 1. Previously it was 2, now it is decremented and it becomes 1. And now when it leaves the critical section, then it must execute. At this moment, for example, even though P2 wanna enter the critical section, because you can see there that P1 is no longer in critical section, so P2 will try to enter its critical section, but before entering the critical section it must have to execute wait, and once the wait is called on mutex, it will fall, because mutex is 0, so it will be in busy wait, and it will be trapped, and it will be trapped until P1 calls a signal on mutex, and once P1 calls signal on mutex, the mutex value will be incremented and it will become 1. Alright, and once this value becomes 1, so P2 notices that and because it was waiting in this statement, and it noticed abruptly that the value of mutex is now 1, and now it will have to release this lock, or this span lock, or this busy wait, and it will have to proceed, and upon proceeding it again decrements, because it was wait call, so it will decrement the mutex and will enter in the critical section, counter will be incremented, counter becomes 2, and finally it will have to leave the critical section, and at this moment once it leaves the critical section, its signal mutex, and mutex will be equal to 1, and now it is free. If any other process want to enter the critical section, then they can, right? And now let us solve this problem with synchronization of emptiness, fullness, and also maintaining the counter correct and consistent. So far, the solution that we just discussed was the mutual exclusion problem, and that was you solved with the help of single semaphore, that was binary semaphore. But what about the whole scenario if we are taking into account the emptiness, so, and we are also controlling the emptiness with semaphore. Similarly, we controlling fullness with semaphore, and we also maintain the correct value of the counter. So now we are dealing with three restrictions, three constraints. The first constraint is that if the list is empty, then no consumer can enter to read the data from the buffer, because reading the data from empty buffer itself becomes a critical section. Another critical section will be fullness, and the fullness if the input buffer is full, then producer process will not be able to produce a character. And in that case, we will have another semaphore that will restrict P2 to our producer to enter the critical section to what, to put some character on the buffer. And finally, the counter variable that will count the number of characters available in the buffer. So how things will happen? For that purpose, we must have to change the existing code structure. So producer problem will look like this. It will produce an element. First, an element is produced, and now this element is just produced, it is not been placed on the buffer. First, it will have to call wait on empty. Wait on empty means, actually what does empty mean? Empty means that how many empty slots are there in the buffer. You can see that if empty slots are zero, then no entry will be made. It will show that the stack is full, sorry, the buffer is full. So it will show that the buffer is full. And similarly, here is another semaphore that is full. This shows that how many slots are filled. How many slots are filled? It just show if it is zero, then it shows that all slots are empty. So it basically shows that all slots are empty. So what we will have to do, we will have to do a trick, and that trick will be that the empty slot will be initialized to or empty semaphore will be initialized to a number of or buffer size. It will be initialized to buffer size. Why? Because initially whole buffer will be free or empty. So initially when all the buffer is empty, and once it is called wait, it will decrement the number of empty, because another character will be produced. It is a produce function, so it will produce a character, and number of empty slots in the buffer will be decremented. So you definitely will call wait operation first. And here the mutual exclusion, all the code inside this that is putting a character on the buffer will be mutually exclusive. And similarly, once they're done, signal on mutex will be called, but signal on full will be called. Signal on full means that now that one element or one character has been placed on the buffer, so we will have to increment the full semaphore that will show that now the empty slots have been reduced, right? And here is the code for consumer. It will first wait upon the full operator, and then upon mutual exclusion and ensure the finally signal mutex, and finally it will signal the emptiness because it will have read some character, and after that it will have to consume a character. So reading a character, it means the removing an element from the buffer, and consuming a buffer, in between there are two release operators, and these signal operations basically ensure synchronization. Mutex will be initially declared to 1 because it is a normal binary semaphore. Just it's a binary semaphore, okay? And empty, that will be initialized to buffer size. It will show that how many empty slots are there. and initially full will be 0. That will show that how many full slots are there. You can see that this is basically decrementing the empty pointer. Let us understand the detailed processing, that how actually this implementation work. So here are two processes, producer process and consumer process. And for example, these are the processes, producer and consumer, and we have a finite, a limited size, a fixed size, and a bounded buffer that is of 6 size. And similarly we have three semaphores: the empty semaphore, and the mutex, and the full semaphore. The empty semaphore shows that how many slots are empty, so initially all of them are empty. The mutual exclusion and shows that whether the process is allowed to enter or not, and initially everyone that comes first will be allowed to enter. And full semaphore will show that how many slots are filled, so you can see that all slots are empty at this moment, so no slot has been filled, so it will be as it is. Now suppose producer process run, and once the producer problem runs, so it produces a character first, and here you can see that a has been produced here. Once a has been produced, then it will have to call await on empty semaphore. Okay, so empty semaphore is waited. It means that empty semaphore's value will be reduced because it is not 0, and once it is not 0, its value will be decremented, and empty semaphore value will become 5. And similarly wait on mutex will be called. So upon wait on mutex, the value of mutex will also be reduced to 0. You can see here the previous value of mutex was 1, and now because wait on mutex has been called, so mutex value has been decremented to 0. And then it will have to put item in the buffer, and the item a will be put on the buffer. Once a is being placed on the buffer, another thing is that signal on mutex. It will have to execute signal on mutex, so the value of mutex will be now incremented, and you can see that mutex become 1. And another thing that is signal on full, so full will become 1. I'm sorry, here, right? So signal will become 1 and mutex will become, both of them have been signaled. And for example, after that consumer, now suppose consumer runs. If consumer runs, then first of all it will have to wait on full. It will have to call wait on full, so a full will become 0 because previously full was not 0. So after running this statement, full will become 0, and now that full is 0, it will have to wait on mutex, and mutex will also become 0 because previously mutex was not 0, and now it becomes 0. And after that it will have to remove an item from the buffer. So for example, the a has been removed, and now a has been removed, and then after that it will have to signal on mutex. But once mutex is signaled, its value will be incremented and mutex will become 1. So another thing is that it will also issue signal on empty. So empty value previously was 5, and now it has been signaled. It means that it will be incremented, so signal will become empty will become 6. And finally it will have to consume item, so a will be consumed, and it will be with the consumer process. Now suppose at this moment both of them simultaneously run. Process P1 and P2 simultaneously run their respective processes. So let's see what will happen. Let me clear this all for you. And in the first instance, you can see that, for example, this step occurs before the synchronization. Actually, I want to test the synchronization. So first P produces B. Another character has been produced by the process P. Now what actually happens is that wait empty and wait full are being executed simultaneously. But once wait on empty is executed by this process, it does nothing except reducing the value of empty. So empty will become 5, but at this moment you can see that this process has been blocked. What? this process, the consumer process, has been blocked at this moment. Why? Because at that moment it was calling wait on full, and full is 0. So if full is 0, it means that this process will be blocked. So you can see that consumer is now in a spin lock or in a busy wait. All right, and as the consumer process has been blocked, the producer will proceed and it will call wait on mutex. So mutex value is 1. One wait is called, its value will become 0. And the third thing is that it will put the item on the buffer. So B will be put on the buffer, and you can see that previously, because one operation has been had been performed and a value was inserted in it, and then that value was removed by the C in the form of A. You can see over here that A was next value will be inserted in the next place, because this time n pointer is here, n pointer is here, and similarly out pointer is also here too. So do not confuse here. And the third thing that will be performed by the producer problem will signal on mutex. So mutex will be incremented, and finally signal on full. It means that full will be signaled and full will become 1. But as soon as full becomes 1, uh, at that meanwhile, consumer process will notice that and will start at execution wait full, because it was waiting for the full to be 1 and now it becomes 1. So it will stop blocking and will proceed, will run the wait function, and when wait on full is called, then full's value will be decremented and will become 1 0. Okay, and another thing that wait on mutex will be called. So mutex value will be 0, and then an element will be removed, so B will be removed, and once the B is removed, then signal on mutex will be performed and mutex will become 1. And similarly signal on empty will be called and empty will become 6. And similarly consume item will be consumed, so B will be consumed. And now you can see that at this moment we are exactly at the we are exactly the values that we had at the start of this of these processes. So this is how producer consumer problem is controlled using counting semaphore as well as binary semaphore. In the previous example we used with the binary semaphore, and we manage how to execute concurrently two processes, the increment operator and decrement operator. In this example, I told you that how can we use three semaphores, the empty one, the mutex, and the full one, to ensure that all three things are realized. The first thing, the mutual exclusion, and the second thing, the emptiness, that no item from the empty list can be read, and similarly the full one, that no item in the full list can be inserted or can be produced. So thank you so much for watching this. In the next lecture, inshallah, you'll discuss the reader writer problem as well as the dining philosopher problem. Thank you so much. Khuda Hafiz.